Morning, guys. So what I wanted to do with you in this lesson here is just to summarize some of the major concepts and themes that we've seen in this kinematics chapter. What I'm going to start off here is just giving you a quick question to practice a position time graph and a velocity time graph, making sure that we're actually able to do the interpretations and a couple calculations, and then we're going to summarize through some of the other key ideas in preparation for your test. So just as a quick warm-up here, I'm going to give you a position time graph, so a DT graph, displacement time as well, is what it's called. I'm going to scale this, let's say 5, -5, so it drops down to -10. Let's say the first segment, it ends up doing this. Let's just go up in increments of 2, going the other way, 2, up to 8 there, 2. We're going to have a curve, let's say it does this. And then afterwards, let's make a curve this way here. So it curves down that way. That's going to be at sort of -5 and 6 there. And then let's get it to go just diagonal like this. All right. So I have a couple time intervals sort of laid out for you. We have A, B, C, D. What I want you to practice for this question here is, again, just make the interpretations. What is the guy doing in each of these segments, A, B, C, and D? When you're describing the motion here, point form is perfectly fine, but what you want to be telling me something is, tell me something about his direction. Is he going forwards, backwards? Tell me something about his speed. Is it constant? Is it speeding up, slowing down? You can identify that. And then follow-up question here, let's say that's part A. Part B of the question here, I want you to calculate the instantaneous velocity. Calculate the instantaneous velocity at 7 seconds and at 3 seconds. Right? So that's a practice of your position time graph. I'm also going to try with you a velocity time graph as well, so a different motion. The velocity time graph here was the newer one here. This one here, remember, it plotted, I have no idea where the guy is starting, but over the next sort of time period here, it's actually telling me his speed through as time ticks onwards. So let's scale this up in 5s here. Let's go up 10 and 20, -10, -20. Remember, for this chapter here, the reason why displacement can go into the negative, it just means behind, right? Whereas velocity negative here means actually going backwards. Although there's going to be curves on a displacement time graph, because we're going to be assuming constant acceleration, there's not going to be any curves on a velocity time graph. So let's just start off here. Let's actually start off in the negatives here. Let's go that way. Let's make it go down to 10, 20. And then let's get it to skip upwards. Let's do this one. And then let's just give it a really weird shape. Let's do this. Right. So although this is also supposed to be a continuous graph here, your speed can change a lot quicker than your position, right? It isn't like, oh, suddenly I'm here and I suddenly run up to here. But your speed can change like that. Your speed can be 10, and then it suddenly ramps up to 20, right? Really high acceleration. So let's say we had that graph there. Again, sort of the same interpretation here. Part A of the question. I can word it to you the other way. So between 0 and 5 seconds, 5 and 10 seconds, 10 and 15, 15 and 20. Can you tell me something about the direction? Tell me the heading. Which way am I going? Tell me something about the speed. Tell me, is it constant? Is it at rest? Is it speeding up, slowing down? You can even comment on the acceleration at some points. And just sort of a couple of side calculations here. Can you calculate the acceleration at 12 seconds? And also I want you to find for me here, find the total displacement between 0 to 20 seconds. So I plotted for you the next sort of 20 seconds of motion. How far does the guy get? Okay. I'd really encourage you just to pause the video, try it out for yourself, see how much of this you remember. And then when you unpause, you can have a look at what we did here. Again, some hints that I do for myself here is whenever I'm faced with these graphs here, Like we talked about here, displacements can be positive or negative. When I'm in the top part here, all it concludes is I'm actually just in front of the starting line. The starting line is actually d equals 0. That's when I'm actually measuring things from. Just because I'm in front, though, don't feel tempted to be like, oh, in front means I have to go forwards, or forwards have to means I have to be speeding up. In front just means I'm standing in front, right? As my displacement drops into the negatives here, sure, I would have had to walk backwards at some point in time, but all it guarantees me here is if I'm lower than the graph here, this part here just means I'm behind. It really doesn't tell me my direction, doesn't tell me my heading. So we actually need to analyze these segments sort of little by little. We need to go, okay, in terms of the direction, the first segment, at 0 seconds, I'm at 5 meters. I'm 5 meters in front of the flag. A little bit later, I'm still at 5. A little bit later, I'm still at 5. Time just keeps ticking onwards. It's the independent variable. Well, I'm constantly at 5. In this case here, I'm actually at rest. And that's because your velocity is actually 0. If you know the number, may as well just give it to me there. So 0. What about between 2 and 4 seconds in segment B here? Well, at 2 seconds, I was at 5 meters. A little bit later, I might be at 3 meters. A little bit later, I might be at 2 meters. I'm at 1 meter, right? As I'm getting closer and closer to the flag, oh, that must mean I'm actually going backwards. So my direction is actually backwards. We're actually going to see that. Remember, one key feature on the displacement time graph here is the slope is the velocity. Depending on how something is slanted, it's actually telling me the speed. So in this case here, again, it's hard to do a slope of a single point. What we did there is just using a tangent. If it slants here, starts going, sort of falling down, this orientation is negative. You'll notice the slant here is not only negative, as you go through this time interval, the slant here starts getting more and more shallow. So it's like my speed goes from, like, I don't know, making up a number here, -10 to -5 to -3, -2. The negative part just tells me backwards, so negative velocity. But if you look at that magnitude, my speed is going from 10, then it's 5, then it's 3, then it's 2. The size of it is actually getting smaller, so this right here should actually imply that I'm actually slowing down. And that's what I mean by speed. You might not need to calculate it unless they specifically ask you for it, but you just want to slow down there. In C, again, we want to know our direction. So at 4 seconds, I'm at the flag. A little bit later, I'm at -1. A little bit later, I'm at -2. Well, I know my direction is backward. Again, you'll notice that the slant is actually going into the negatives again. So we know our direction, again, is backwards. We have a negative velocity here. And in this case here, we can do the sort of the slantedness here. Well, we're going from a sort of more shallow slant here. As I step forwards, I notice that my tangent actually gets more and more steep. This could actually mean speed up. The other way you could sort of interpret that here is you can use that staircase analogy. Give me an increment of time, I get yay far. Give me the same increment, I get yay far. Same increment here, I get yay far. You'll notice that I'm getting farther and farther distance for as time ticks onwards. I'm actually speeding up. Again, wrap your head around that there. My direction is actually backwards, but I can be speeding up, no problem, right? So velocity is totally separate from acceleration. In part D here, I continue to move backwards. So I'm going -5, now I'm -6, now I'm -7, -8. I'm getting farther and farther away from the line. I know it's backwards. That's not because I'm in the negative region, right? We were going backwards in B as well. But I know I'm going backwards because my slant is actually negative. This time my slant is actually just a nice constant slope there. So we have a constant negative velocity. Constant just means it's a velocity that stays the same. Constant doesn't necessarily mean 0. Right? Then let's calculate here. Calculate the instantaneous velocity at 7 and 3 seconds. Instantaneous velocity is the speed at one particular instant. They want you to calculate at 7 seconds. So let's find where 7 seconds is. 7 seconds is right here. Again, usually it is very hard to find the slope of a single point, but you'll notice we had said between 0 and 8 seconds here for segment D, your speed is actually constant. So we can choose any 2 points that are easy to read. Say I have a coordinate here. This coordinate here is x-axis of 6, y-axis of -5. This bottom coordinate here is 8, -10. And then we can just calculate for 7. We can go y2 minus y1, x2 minus x1. That would give you your slope. So it doesn't matter which point you call which. Let's call this point 2 if you want. -5 minus a -10. Then we have 6 minus an 8. Let's see what speed that gives me here. -5 plus 10 is 5, divided by -2. So -2.5. It's a little bit hard to read sig figs from a graph, so just keep it 2 or 3 sig figs, but make sure you have the units. At 3 seconds, it's a little more interesting. At 3 seconds, we were sort of in the middle of this slowing down region. 3 seconds similarly only gives you one single point. What we had to do was we actually need to do a tangent. Our tangent line here is actually going to be a line that basically follows your curve. I want it in such a way that if your curve does this, right? 3 seconds is just one single point in your graph. I want my tangent to practically follow the curve here, so that if you zoom into it, the slope of the tangent essentially measures the slope of the curve itself. So depending on how you draw your tangent here, let's choose 2 points that are easy to read. So maybe my tangent here, maybe in the green here. In the green, it looks like it's going through here, 2, 5. So that's one of my coordinates here. Maybe the other coordinate here is not quite the 4 here. Maybe, I don't know, 3.4? I don't know. 3.4, that's my x-axis, and 0. I would just pick 2 points that are easy to read, and then again, y2 minus y1. For 3 seconds, I would then go, say, 0 minus 5 divided by 3.4 minus 2, negative 5 over 1.4. So 5 over 1.4 gives me a speed of, give or take, negative 3.6 or so. Right? And that's how you find the instantaneous velocity. I didn't ask for it this time, but you can also calculate an average velocity as well. For an average velocity, it's the slope of the secant. So what I do here is for average velocity, let's say I wanted to know the average velocity between 0 seconds and 8 seconds here. I know there's all these little complexities, there's all these little blips. I'm at rest for a little while, and then I do a slow down and a speed up region here. What average velocity is sort of that blindfold analogy. When I'm blindfolded, I see that you are at 5 at the beginning. I'm going to give you 8 seconds when I'm not watching. When I take off my blindfold at 8 seconds, I realize you're at negative 10. What average speed, what sort of straight line fit would I have to be going at so that I can get to that position in 8 seconds? And all you would do is you take those 2 points, you calculate the slope, you do something like, well, this is dropping by negative 15, this is over by 8. In that case, there, your average velocity over the 8 seconds is going to be negative 15 over 8. At probably no point in this curve here, or very little time, was I actually traveling at average speed of, let's say, negative 1.9 meter per second. But that would be the speed that, if had you not done the staying put and then speeding up, slowing down, had you not done all these little changes in speed here, you would at least need to be heading back 1.9 for 8 seconds, so that when I take the blindfold off in 8 seconds, you are now 10 meters behind the line. You're 15 meters from where you started, but you're 10 meters behind the flag itself. So for average velocity here, it's the slope of the secant. Let's just switch over to the other graph here for a velocity time graph. Again, this one here generally is a little bit harder to understand because what we're plotting is not his whereabouts. We're plotting his speed as time goes onwards. Again, the way I think about this here is, if my velocities are positive, if my graph is anywhere above, positive velocity must mean you're going forwards. It doesn't matter the shape. It doesn't matter if this is climbing. It doesn't matter if it's straight across. It doesn't matter if it's falling there. As long as you're up above, it means forwards. So between 10 and 20 here, we know this is forwards. We know this is forwards. So those are both going to be positive velocities. On the bottom of the graph here, this part here, your velocity is dropping into the negatives, negative 5, negative 10, negative 20 or so. When your velocity is negative, that implies here that must mean backwards. So in terms of interpretation, in terms of which heading I am going, those are forwards. These ones here are backwards, BKW, and this is negative velocity. Now again, that's just the heading. That's just sort of which way I'm facing. My speed might still change. So let's see what's happening to the speed in all these segments here. Between 0 and 5 seconds here, my speed at first was negative 10. I'm walking backwards 10 meters per second. At 1 second, I'm still walking backwards. At 2 seconds, I'm still walking backwards. Although you may say it's a constant velocity, you are actually walking, right? Sometimes people like assuming, well, constant means 0, right? Constant means I'm not moving. Well, I am definitely moving. What's constant is actually my rate of change. So I'm actually not speeding up or slowing down. I'm just walking back at a constant pace. Then what happens between 5 and 10 seconds? At 5 seconds, I was going at negative 10. A little bit later, I'm going at negative 12. A little bit later, I'm going at negative 14. The negative part, right, I go all the way down to negative 20. The negative part just tells me the direction. I already dealt with that part. But again, the magnitude part, if my size goes from 12 to 14 to 20, right, my number is getting bigger, this must mean I'm actually speeding up. Again, the temptation is, oh, I'm going backwards, I'm actually slowing down. No, the backwards is the direction, but the speeding I'm slowing down is the acceleration. Those are two totally separate concepts. Now, as I switch over into the forward region here, right, I'm going up into the positives here, my speed from 10 to 15, it goes from 0 to 2 to 4 to 5. Again, the magnitude is increasing. That part there in the middle also means speed up between 10 and 15 seconds. Then it suddenly jumps from a speed of 10 to 20. And for the last 5 seconds, it goes 20 to 19 to 16 to 14 to 12, right? The size of it is getting smaller. This part here actually means slow down. So just like going forwards doesn't always have to imply speeding up, backwards doesn't imply slowing down, you have to analyze these parts here sort of separately. The sort of things that we can calculate here, we'll get some practice with these questions here. If you want to find the acceleration on a velocity time graph, acceleration is the slope. Earlier, the slope was the velocity on a position time graph. The slope is acceleration. At 12 seconds, again, nicely for this graph here, we're not going to have any curves, so it should be a little bit easier to find the 2 points that we need. Our coordinates here are maybe 10 and 0. That's an easy point to read. The other point is maybe 15 and 10, right? I can do y2 minus y1, so 10 minus 0 divided by 15 minus 0. 15 minus 10. This gives you 10 over 5, so my slope is 2 meters per second squared. That is my acceleration rate. When I have an acceleration, I expect my speed to be changing. And in that case there, you'll notice in segment C, I'm going positive velocity, and my acceleration is positive. When those point in the same direction, we implied speed up. So that's consistent with this logic here. Perfect. Then calculating total displacement a little bit harder. Displacement, we're actually using the formula here, d is equal to v times t. This is actually the area that's bounded by the curve. The area on a position time graph doesn't do anything, okay, but at least area on a velocity time graph. What we're doing here, we can see it really well here for this segment. If I was going at negative 10, for every second I travel, I get negative 10 meters. I go backwards 10 meters. If I do that for 5 seconds, it should just be negative 10 times it by 5. Oh, I get an area of negative 50. Right, that's how far I go. What if I start getting areas that are sort of trapezoid shapes like this? You can break it up into a square and a triangle. This square here would also be an area of 50. This square here, half base times height, is an area of negative 25. Those areas are all negative. These would take you backwards because we knew our heading. As we switch over into the positive bits here, this part here would also be sort of base is 5, the height is 10, so half base times height is going to be a positive area of 25, right? That's also going to be a 25 there. This one here is going to be a 50, but those are all positive numbers. That's how you show your work, just calculating the areas there. So therefore the areas, we do the negative 50 from the beginning. Then we get negative 50 for just for that square with the negative 25, so that's negative 75. We're going to do the 25 for the purple square here, that's positive. And then we're going to do the 25 and 50. So in total, we're going to have 75. So we just add those up, and we'll see what we get here. Negative 50, basically plus 25 here. That gives me a total displacement of negative 25. So over these 20 seconds here, you end up, you walk backwards farther, then you start coming forwards, but in total, you are still 25 meters behind your initial point. Not necessarily where the flag is. You could have been way far in front of the flag, you could have been behind the flag here, but relative to where you were standing, having walked backwards and walking forwards, you haven't quite made up the difference here. You're still a little bit behind of your starting point here, right? So a lot of this chapter here was just looking at those graphs here, was analyzing. Those graphs had the advantage because they actually give you all the little details going in between the segment. If you now compare, as you do a quick overview of some of the major concepts here, as you start using those kinematic formulas, kinematic equations again, we were doing this blindfold on, blindfold off analogy here. We may have set initial here, we may have set final here, and we sort of avoided the complexity in the middle. So at least the graphs here give you that detail. So what we're going to switch over here is just a quick page here on just some summary notes here. This was our first big chapter, which was kinematics. Kinematics is essentially the study of motion concepts like displacement, like velocity, time, acceleration, right? We saw sort of the interplay between these ones here. We began this chapter looking at what's the difference between either scalars or vectors. They always like saying scalars have magnitude or size. A vector has both size and direction. So to represent the size of a vector, we can actually look at the length, how long the arrow is. That's actually given by the size. And then the direction is just sort of which heading you have. Let's just go over our conventions again. If this is a top view problem, if you're sitting in a helicopter looking downwards, when you have northeast, southwest, our positive directions are north and east. Our west and south are going to be negative. If this were a side view problem, if you're looking at your TV screen, for a side view problem, we have up to the right, we have down, and we have left. We always do what's called a right-handed coordinate system, so that right and up are positive, and then left and down are negative. So we saw us pretty sloppy through the chapter. Oh, let's just add a negative. Oh, let's take away that negative, because the negative just indicates for you the direction. So even if you give you, let's say later on, oh, my displacement here is 10. Well, I thought displacement should be a vector. Well, because the 10 here is itself a positive number, using these conventions, positive means forwards, positive means to the right, that actually is the direction. Or you could say in words, we are 10 meters to the right, or 10 meters east, or whatnot. So even though it's going to look a lot like distance, right? Oh, it's just 10, it's just the size. But just using the sign positive or negative, it actually indicates to me the direction that I'm heading. When are the scalar form and the vector form the same? So let's just do this here. The distance and the displacement, just as an example. Distance is the scalar, displacement is the vector, are the same if there is no change in direction. Well, the big difference between a vector and a scalar was, oh, it has direction. I care about whether I'm going forwards or backwards. If there is no change, then of course they're the same. So same sort of analysis between speed and velocity. Those are the same as long as there's no change. Unfortunately for us, most times there actually is going to be a change. One nice thing here, that's a scalar. So scalars don't have direction. One nice one was time. Time is a scalar. Time is just a value. Even though time sort of ticks forwards, we still say, well, you can't turn left in time here because time is a scalar, especially when we got to those projectile motion questions, when we sort of set up, here's an x column, here's a y column. Because time didn't have direction, time can actually jump between columns, where the other variables like acceleration, like displacement, those ones couldn't. So that's actually the advantage of scalars. For the first couple of chapters, we dealt with vectors. So kinematics, we're going to go through a chapter on forces. Forces are also pushes and pulls, acceleration. Those all have direction. Eventually, we'll get to a unit on energy. Energy is a scalar. It's going to be a lot simpler in terms of adding, subtracting. We just practiced through some questions for displacement time, also called a position time graph, because it tells you your location through the time. We talked about here the most important notes here. The slope is the velocity. There's two types of velocity. We can do average velocity. Basically, it's a connect the dots. It's a I know in this case here you were walking forwards. I know your speed was actually changing. But if I was blindfolded at the beginning and I'm blindfolded afterwards, what average speed would you have to go at? It's going to be a little bit slower than your fastest speed. It's going to be a little bit faster than your slowest speed, so that you can get that distance away from me, delta d, in this amount of time. So that's going to be your average velocity. And so for the other velocity, it was instantaneous velocity. Again, velocity is still the slope. However, the problem with instantaneous velocity is we only have one instant in time. If I only have a single point, I can't find the slope of a single point. So what we did is we ended up using a ruler. You would draw what's called the tangent line. This is basically a straight line that essentially follows your curve, so that if I zoom in really, really close, my curve should basically overlap with the tangent line. Once you have your tangent line, you can choose any 2 points that are easy to read, because that tangent here actually doesn't change the slant. Choose those 2 points there. We do that rise again. Remember our formula, y2 minus y1, x2 minus x1, and that would help approximate an instantaneous for us there. That's why they're saying the slope of the tangent is instantaneous velocity. So lots of curves for your position time graph here, not so much for a velocity time graph, because velocity time graph, we were assuming uniform acceleration. So there's our word here, uniform acceleration. I know early on in this chapter what we did is we started saying, what if I travel at this speed for a shorter period and then I change my speed for a longer period? That was just for our curiosity's sake here at the beginning. For most of the equations, these are the ones that are on your formula sheet here. For most of them, we are going to be assuming constant acceleration. So how I deal with this one here, equation number 1 was our basic motion equation. This basic motion equation was actually a slightly simplified form. Basic motion assumed that there was no acceleration. Not only are you uniform, are you constant acceleration, what if a is actually 0? This basic motion equation actually comes from equation number 4. If a is actually equal to 0, half times 0 times anything here, it's just going to be 0, and we're just going to get d is equal to vt. If there is any indication of acceleration, however, we can't just use a basic motion d as vt. We'd be losing out this a term. So what we did right away is we went through these 3 kinematic formulas. You do have these on your formula sheet. Just be careful. You can still use either vf or vi, but make sure when you just look on your formula sheet here, let's say that first formula is written v is equal to v naught plus at. Make sure you can read this notation. If I don't have that naught symbol, that means final velocity. Usually, whenever you see this naught symbol, it means something is the initial. We saw a problem or two that sort of was compromised. If I didn't really want to use these equations here, I could sort of get away with a v average, but usually I just keep things simple in my head here. If there's no acceleration, d is vt. Like for example, a projectile motion equation, there is no horizontal acceleration. There's no speeding up or slowing down when I'm flying through the air. I just use d as vt. But in the y column here, because I know there's always an acceleration due to gravity, I'm down to using these 3, 4, 5. I really don't use that equation 2 all that much. So I just define all these terms for you here. Just a comment on units. So make sure we are in SI units. So we did that section on prefaces. Make sure everything is SI. The most common one that's problematic is they give me a speedometer reading that's in kilometers per hour, like 50 kilometers per hour, 80 kilometers per hour. Before you use any of these equations, you want to convert it into the SI units. Because we do this conversion so much, the conversion is 3.6. You need to divide by 3.6 to convert something kilometers per hour to meter per second. If they want the final answer in kilometers per hour, you just multiply 3.6. You can look back at our conversions lesson to figure out where that 3.6 came from. So make sure everything is in SI units here. Acceleration has a funny set of units. Acceleration is defined as delta v over delta t. Whenever we see that delta symbol, the delta means change in. It's sort of a comparison. And what it's going to be is it's always going to be final minus initial. So in this case here, what we're interested in is how does your speed change, right? I go 0 to 50, right? The top part there, if it's the correct SI unit, should be meter per second. And I'm going to divide it by another thing that's measured in seconds. If I go meter per second divided by a seconds, you can think of that one there, meter per second times the reciprocal, which is 1 over seconds. And therefore, the units is meter per second squared. So you can keep it easy for yourself for dimension analysis. If you see something like meter per second squared, that's giving you an acceleration. Remember in that case there, although velocity and acceleration are separate concepts, whenever the velocity and the accelerations were pointed the same way, that meant speed up. Whenever your velocity was trying to go one way, but there was a wind blowing the other way here, whenever these are opposite of each other, that ended up meaning slow down. In words of slowing down, we call that a deceleration. A deceleration is just another way of framing a negative acceleration. Let me write that down here. Deceleration, it actually is acceleration, but it's acceleration in the negative direction. Negative acceleration, negative to whatever you're doing. So if I'm trying to go positive, acceleration is negative. I could also be trying to go negative. My velocity is -5, and if acceleration is positive, as long as they are in opposite direction, it ends up slowing down. So if they oppose each other, slow down. If they're with each other, they speed up. We talked about doing a velocity time graph. We practiced that earlier here. Couple keynotes here. The slope on this graph is acceleration. This is always going to be there's no curves or anything like that, so it should be fairly easy to find slope, whether it be an instantaneous slope or an average slope there. The other one here is area under the curve. When we say area under, yes, when the graph is above, it makes sense here. Well, this is the part that's under the curve here. If this velocity graph here actually drops into the negatives, so if I have a VT graph here, let's say it does something like this, I don't mean the literal area underneath. I'm actually talking about the area that's always bounded by the curve. So let's say I have a velocity time graph here. The area I'm talking about here above, it makes sense. Well, these are positive areas. Positive areas means I actually am gaining ground forwards. And in terms of my negative area here, areas down here are going to be negative. You notice that it's the area that's sort of bounded. It's between the curve and where the x-axis is. If the area is negative, I'm actually losing ground here. I actually go backwards. So backwards. All right. And we can do some calculations with acceleration, displacement. We then took a detour to take a closer look at vectors. We saw that especially for our two-dimensional stuff here, anytime you needed to compare x and y, you need to piece it back together to the hypotenuse, we needed to use Pythagoras. And in fact, how we shortcutted it here, I want you to be comfortable enough that you can say the hypotenuse is the root of a squared plus b squared. That way I'm not having to write out the whole Pythagoras and then do the square root later on. That just saves you a little bit of time. Our math note here, we can say SOHCAHTOA for our trigonometry practice here. Depending on the different sides, everyone knows the hypotenuse. Hypotenuse is going to be the longest side. The longest side is always the one that's across from the right angle. Depending on the angle, we're going to typically use theta for it. Theta is just the Greek letter that we use to as a placeholder for the angle. The angle, if you imagine it to be an eyeball, the side that you're looking at is always the opposite. The other side is going to be the adjacent, and then we have these relationships here. For a lot of our vector addition stuff here, we ended up using tan. So tan theta was opposite over adjacent. If I undo the tan, I have theta is equal to inverse tan of opposite over adjacent. And then we use that notation, not just something like northeast. I actually need to tell you north of east or east of north. And depending on which direction I was heading, let's say this is heading in the pure east direction, and I start aiming in the northward direction. In that case there, I'd call that angle north of east. On a multiple choice, you might not find it as north to east. Remember, angles are complementary. Angles have to add up to 90 degrees. If this is, let's say, 20 degrees north of east, I can go 90 minus 20. Oh, this is 70 degrees. This time 70 degrees here is actually lined up. It's going eastward from the pure north direction. I can call that east of north. Just be careful that these ones here are complementary. They add up to 90. For vectors, the order doesn't matter. You can do go east first and then go north, or you can go north first and then go east. It would still end up in the same spot, but the triangle that you end up drawing might end up giving you one set of angles instead of the other angle. As long as you do the angles as complementary, 70 degrees east of north is 20 degrees north of east. Those will point you in the same direction here. When you add vectors, they have to be pointed head to tail. So you're noticing after I walk to the east, I'm now standing here. Imagine plopping another coordinate system here, and now you go north from there. Never add vectors so that they're sort of, oh, I walk east and then now pretend I'm back there and now walk north. That doesn't make any sense. So make sure things are added head to tail. They can't also be, oh, I'm going to add head to the east and then somehow add head to head. That also is incorrect. So head to tail whenever you add vectors. We found that we actually, when we were doing these problems here, if a vector was just purely in one direction, was fine. For some things that were in a diagonal, I would need to break up into x and y components. So let's say this is y1, there is no x1. This is y2 and x2. Your whole notion of vector addition. We'll practice this more in the momentum chapter again. For vector addition, what we're trying to do is we actually have to break any diagonals, break into x and y components. And the key feature that we actually utilize for projectile motion, I have it typed for you here. The x part of the motion occurs as if the y didn't occur. They're completely independent of each other. So now if I tried to add these vectors, if I tried to do y1 and I tried to do this other diagonal, diagonals are always really hard to add because they're off at some random angle. But what I'm going to do is I'm going to break up the x and y so that I can later on add up the x's. I can just go x1 plus x2. I can add up the y's, which is y1 plus y2. I can add up the things that are left and right as if the north and south didn't happen, and vice versa. We talked about if we're on the Earth's surface here, the acceleration due to gravity is negative 9.8. That negative there just implies downwards. There was a problem or two that I actually redefined downwards as actually positive. That was sort of like, if I have an object and I know this object is just going to fall, well, why say velocity is negative and acceleration is negative? Why not just redefine both of those as positive? And we know that's a speed up case here. The velocity is 0 at the maximum height. We still consider that a free fall problem. Take an object, you throw it to the top. My velocity is positive. My acceleration in that case there would be negative. It's going against me. It's going to gradually slow me down, slow me down, slow me down. By the time I get up to the top, you actually do know the final velocity here is 0, at least in the y direction. So that came into play in some of our equations there. And especially when we got to the two-dimensional kinematics here, we dealt with a couple styles of problems. We dealt with a meatball problem. We dealt with a football question, right? We had to separate the two columns. The thing is, those kinematic equations we've been doing, they only work in one dimension at a time. So just make sure you don't accidentally cross over the variables there. So let me just leave you with a football question just for practice here. Cannonball was even harder than this. But a football style problem, let's imagine I have the football on the ground. Let's launch this football here at 50 meters per second, so quite a kick. The angle, let's make it 30 degrees. This football is going to go up to the top and then downwards. I wanted you to do a couple things to this problem here. Part A of the question, when you're defining sort of where's initial, where's final, just deal with max height. So find for me things like how high off the ground is this D? Right, what's that displacement there? Find for me the range. Remember, the range is the how far in the x we would have gotten. And also calculate for me how long did it take for me to fly there. So the time, how long does my clock say there if t equals 0 was right here? That's for part A of the question. Part B of the question here, let's do the total hang time. Hang time, remember, is the total time it's in flight. And therefore, I can ask you very similar questions here. I know in that case, my D is actually going to be 0. I'm no higher or no lower than where I started. So d is equal to 0. However, I can ask you questions like, again, what is the total, what's the total range here? Let's call that distance here x2, right? Based on the symmetry, it is going to be double half of it there. So x2 there, what's the time? How long does it take you to get there? And let's also calculate the final velocity. What's the VF? Remember, for kinematics here, when you calculate final velocity, this is always the velocity right before hitting. Right? So it's not after it collides and after it loses all its energy and it's now stopped. Oh, now it's 0. This final velocity is the speed before it actually hits the ground. So I'll leave you with that question there. You can try it out for yourself. Just let me hint at it. First part of the problem here, I can't deal with this 50 because it's an annoying diagonal. What you're going to do is you're going to break up how much of it is x, how much of it is y, so that I can have, here's what I know about x, here's what I know about y, make a list of your variables. Remember, we always assume that there's no air resistance, so the acceleration in the x is going to be 0. And I'm going to make that note here. Assume no air resistance. Keep things simple for yourself unless they tell you otherwise. Air resistance is sometimes known as a drag force. You can play around more with the simulation and verify some of your answers there. All right? So hopefully that overview some of the concepts. Keep practicing your way through the questions, and we'll pick it up from there. Thanks, guys.